Hi, welcome to the fifth weekly live session of the NPTEL course of River Engineering. This is brought to you by a combined initiative of NPTEL and the SWAM scheme. This course has been tutored by Professor Subhashish Datta from the Department of Civil Engineering at IIT Guwahati, and I am Abhishek Chakraborty, the TA assigned for this course under the Prime Minister's Research Fellowship Scheme. I am a PhD student from the Interdisciplinary Center for Water Research at IISc Bangalore. So, as you all know, I have been continuously uploading the videos of the weekly live sessions on our YouTube channel. So please feel free to check that. I mean, in case you miss out on something during the class, and the the documents related to the course are being uploaded in a Google Drive folder, and I will make sure to record them immediately after the class gets over. So today's class, I believe that it would be better to discuss a few questions related to the assignments, uh, so that whatever doubts you had could be easily solved or sorted out. So I've just chosen five different questions, and then I would be finishing off uh, with a part on the Saint Venant's equation and depicting how the integral from Saint Venant equation works. So let's read the first question. It is a fluid having density is equal to 1000 kilogram per meter cube and kinematic viscosity rho nu is equal to 0.401 meter square per second, flows at 0.2 meter cube per second through a conduit where K is 0.30 mm with a cross sectional area of 0.031 square meters. The depth of water is maintained at 200 mm. Calculate the relative roughness. We have solved a few such questions in the assignments, but I have been getting some mails about difficulty in solving them. So, although it's a very easy question, but still we will try to solve. Sorry. Yeah. So, density is 1000 kilogram per meter cube. The kinematic viscosity is 0.401 meter square per second. Q or the discharge is 0.2 meter cube per second. K is 0.30 mm. The cross sectional area is 0.031 square meters. And the depth of the water in the cross section is maintained at 200 mm. Now to find out the relative roughness, we don't need any other parameter except this K and the D. So the relative roughness can be R roughness relative is equal to small k by D, which happens to be 0.30 by 200 mm by mm, so that it becomes dimensionless. So it would be 0.0015. So this was the answer to the first question. A very similar question has been asked in assignment number 4 or 5. So this is how it is to be solved. Now the second question is again, I believe, was asked in assignment number 5, but I have altered the values just to explain how it is to be calculated. The question states that a stream is flowing in a reach with a slope of 1 in 2500. If the discharge is measured to be 35 cubic meter per second, calculate the stream power per unit of stream length in watts per meters. So the bed slope happens to be 1 by 2500 or 1 in 2500. Uh, the discharge is 35 meter cube per second. Now let's see what's the stream power. Stream power per unit of stream length. We know it's denoted by omega 1 and can be rho g qs, where rho g is the unit weight of water. So someone is trying to enter. Just a second. So rho g is the unit weight of water, which we know as rho times g, that is 9.81 times 1000, because the density of water happens to be 1000 kilogram per meter cube. Slope we know is 1 by 2500, that is the slope. So it's a straight away formulation. Omega 1 will be rho GQS, which is equal to rho is 1000, G is 9.81 meter per second square, Q is given as 35 meter cube per second, and S happens to be 1 by 2500. It comes out to be 137.34 watts per meters. Let's move to the next question. Okay, so this question was pretty controversial because in assignment number 4, the solution to this question, I mean, this type of question was incorrectly given. So I thought of taking all the generalized conditions to explain how the celerity is computed for a triangular cross section, for a trapezoidal cross section, and for a rectangular cross section, which happen to be the three most prominent cross sectional areas for open channel flow. So we know that the celerity is calculated as square root of GD, which is the denominator expression of the Froude's number. D is the hydraulic mean depth, so D can be represented as A by T, where A is the cross-sectional area of the channel, and T happens to be the top width of channel. In some of the books, D is also represented as L, that is the characteristic length, but it means the same, by the way. For example, while calculating the Reynolds number, we have this rho v d by mu. D is actually the characteristic number. It happens to be the uh, diameter of a pipe for a pipe flow. For flow in uh, flow of water in the porous medium of soils, the characteristic length D will be the diameter of the soil particles, and so on and so forth. So it varies a lot for uh, different types of flow configurations. Okay, so let's see a case of a triangular notch with 90-degree angle. So this would look like this. This happens to be the free surface. Okay, so the total angle, the notch angle is 90-degree. So half of that angle, because of because of because of half of the section being equal to theta by 2, it would be 45 degrees. So since it's 45 degree, we know that the side would be 1 is to 1.
Sir,
Yes,
excuse me, sir. Sir,
yes,
I have a question actually.
yes, please ask.
Uh, what's the celerity of a small disturbance? Like one question was there in the question number, assignment number 4, question number 5. That's what's the celerity of a small disturbance in a channel of irregular cross section?
Okay.
The same equation we have to use there
The
also.
equation is to be used as the same, but the options are incorrectly given. So there is another TA for this course from IIT Guwahati, Mr. Mridu Bhavan Deka. I discussed it with him that the options are incorrectly given. So he has applied for re-assessment of the assignment answers, and hopefully NPTEL IIT Madras will be extending the deadlines for assignment number 4. I mean, wherever this question goes. So we are going to alter the question so that it becomes more clear. Okay.
Okay, so the equation is root GD only.
Yeah, where D is the characteristic length or hydraulic mean depth, and D happens to be
Okay,
A by T.
okay, okay. Thanks, sir.
So there, I think the wrong option of square root of GD square is
Yeah,
given,
it's GD square. It was
and that
given
does
root
not make
GD
any
square.
sense. That does not make any sense because the dimensional similarity is not achieved. C is supposed to be in meter per second, And if you do square root of GD square, that would be meter per second square times meter square. So it would be uh, m to the power 3 by 2 times second, so by second. So I mean, it doesn't make any sense according to the dimensions, right? So the option given was wrong in that assignment. That is why I thought of, I mean, I've been asked by several other people to discuss about that question. So I thought of discussing it here. So in case your option has been marked as wrong, we are actually trying to extend the deadline, or extend the deadline for this assignment to 29th of August. So Mr. Mridhu Bhavan Deka has already sent a mail to
They
NPTEL
have
IT Madras.
valued the assignment itself.
Yes, yes, I mean, no need to worry. I mean, for other courses, in case the options are incorrectly given, then there is an option to increase the deadline. So we plan to postpone the deadline to 29th or 28th of August. So no need to worry about that. He has already, I mean, Mr. Mridhu Bhavan Deka, the IITG assigned TA of this course, has already, I mean, discussed about it with NPTEL IIT Madras. So this mistake is coming from NPTEL IIT Madras team, by the way, not from our side. Okay. So shall I continue, or is there any
Yeah,
other
sir.
question?
Sir,
Okay.
please,
Okay.
please. Thank you.
So the flow depth happens to be small d. Let us suppose it's small d. It's 1:1. So we need to find a by t. So a will be nothing but, for a triangle, half into base. So base will be, if it's d, then it would be d2, and this would again be d. So the base will be d plus d, that is 2d, times the depth, and depth will be d. So it will be d square, area of this type of cross section. The top width will be d plus d, that is 2d. So C, celerity for that kind of a channel would be G, A by T. A is d square by T. T is 2d. So that is square root of G d by 2 for a triangular notch with 90-degree angle. Now let us just move and take a very generalized condition. What would happen if the notch angle would vary for a triangular cross section? I will take another slide for that. You know that the theta can vary. It will not always be. I mean, in practical situations, it will not always be 90 degrees. So let's take a very generalized case. So let us general case for a triangular cross section. Triangular cross section. So this triangular cross section will look like this. This is the free surface level. Let us suppose the depth of the flow is again d, small d, right? And let us suppose the angle subtended by the notch happens to be theta. So due to so this would be theta by 2, very easy to understand, and this would again be theta by 2. Okay, so let us just take out this triangular section and magnify it. So the depth of the flow will be like this d. This is theta by 2, and let us suppose this is x. We don't know what x is, but we want to know what x is. So let us take the tangent of the theta by 2 angle. Tan theta by 2 is x by d. So this gives that the unknown x would be d tangent of theta by 2. So the celerity, we know the equation happens to be the same, g square root of a by t, square root of g times a by t, or d. So so a is half times the base. So the base will be, since x is d tan theta by 2, this will be d tan theta by 2, and this other part will again be d tan theta by 2. So area will be half times the base. Base is sum of d tan theta by 2 plus 2 d tan theta by 2 times the height, and height is d. We know it very well. So it comes out to be d square tan theta by 2. And the top width will be nothing but d tan theta by 2 plus d tan theta by 2 equal to 2d tan theta by 2. So celerity happens to be square root of g a by t. So it would be d square tan theta by 2 by t is 2d tan theta by 2. So it comes out to be square root of g t by 2. So what do we observe from this? That for a 90-degree notch angle also the celerity was same, square root of g d by 2, where d is the depth of the flow, and it is same for every cross section, subtended angle for the triangular notch. So irrespective of the subtended angle, uh, since this tan theta by 2 term gets cancelled, irrespective of the subtended angle, magnitude of the subtended angle, the celerity remains to be same. So we learn from this is that for a triangular cross section, the celerity is same for every notch angle. So this was the case for a triangular cross section. Let's see what would happen for a trapezoidal cross section. Does it depend on the subtended angle or not? So I will take another general condition for a trapezoidal uh, cross section, because the trapezoidal cross sections happen to be the most prominent open channel flow cross sections. So I'm taking another general case for trapezoidal cross section. So let us suppose this looks like this. The trapezoidal cross section looks like this. It is a free surface level. The depth of the flow we are assuming to be again small d. Let us suppose the subtended angle is theta. So this other angle would be 90-degree minus theta. Same with this part also, theta. So this would be again 90-degree minus theta. So let us magnify this triangular section. So this triangular section would look somewhat like this. So let us suppose this x, this part x is x. The depth of the flow we know is d, small d, and this angle is 90-degree minus theta. So let us take the tangent again, just as the case we did for the triangular cross section. So tan 90-degree minus theta is equal to x by d. Someone is trying to enter. So tan 90-degree minus theta is x by d. So tan 90-degree by theta is nothing but cot theta. We know it very well, and it is x by d. So x comes out to be d cot theta. So this part is d cot theta, and this part is again d cot theta. And let us suppose the base is b of the trapezoidal section. So the celerity will be again the fundamental equations are same, g times square root of g times a by t, where a for a trapezoidal section is half sum of parallel sides times the height or depth, whatever we call it. So a will be coming out as half the sum of the parallel sides. So the bottom side is b plus the top side will be b plus 2d cot theta. It's very simple to understand, and multiply it with small d. So this would become 2b plus 2d cot theta. So it will be written as, multiplying by half, it will be written as b plus d cot theta times d is the area of the cross section for a generalized subtended angle. Similarly, the top width will be b plus 2d cot theta, because it's b plus d cot theta plus d cot theta. So this implies the c will be found at as square root of g times a by t. So it is b plus d cot theta by t. T is b plus 2d cot theta times t. So we get an inference that trapezoidal cross sections contain the term theta. So in general, the trapezoidal, the celerity of a trapezoidal cross section happens to be a function of the subtended angle. So C is a function of the subtended angle. That is what I wanted to infer from this generalized example. Now let us take the third most prominent kind of cross section, which is a rectangular cross section. So let us suppose the base of the or the width of the rectangular cross section is capital B. Case of rectangular cross section. Let us suppose the base is capital B. This is the free surface level, and small d happens to be the depth of the flow. So we again need to find a by t, because c happens to be square root of g a by t. So a by t will be nothing but the cross sectional area b times d by t. T is b for the top width. Top width of a rectangular cross section happens to be b, so it is d. So the expression for the celerity for a rectangular cross section happens to be very simple, square root of gt. So using this example, I took first of all, we solved this question for a 90-degree notch angle for for a triangular cross section. Then we took a generalized triangular cross section, and we learned that irrespective of the notch angle, the C will not change. Notch angle may be anything, but the C will remain same for a triangular cross section. However, for a trapezoidal cross section, the celerity happens to be a function of the subtended angle. And for the case of rectangular cross section, it's very straightforward. A by T happens to be the depth of the flow. Let's take a question to understand what would be the abutment scout depth. So we have been given that a 200-meter long bridge is to be constructed in the sandbed channel of a river with 380-meter long span through abutment. The design 100-year flow discharges 1000 cubic meter per second with flow velocity 5 meter per second. If the depth of flow upstream of the piers is 3.25 meters, estimate the abutment scout. So first of all, we need to know. Sorry. So first of all, we need to know what would be the approach Froude number. Let us denote it as Fr1 would be the velocity by square root of g h1. Why h1? Because it's a rectangular cross section, and the celerity for rectangular cross section, as I already showed in the last slide, is square root of g times d. D happens to be the depth of the flow. Here we are denoting it as small h1. So it would be 5 by square root of 9.81, which is the g, times 3.25, which is the depth of the flow upstream. It comes out to be 0.89, the approach Froude number. Now let us check what would be the ratio of abutment length LA to flow depth H1. LA by H1 will be so the length is 380 meter long span, so it will be 380 meter by h1 we have found to be given as 3.25 meters, which comes out to be 116.92 the ratio. So we need to check whether the abutment scow depth is calculated for LA greater than 25 times depth of the flow. So straight away an equation is given for it. We will take another slide to understand it. So square root of z, or the scow depth, will be 4 h1 times fr1 power 0.33. So this equation you will find somewhere in the videos of unit 4 of the unit 4 or unit 5, unit 5 most probably, of the lectures. So it's 4 times 3.25 times 0.89 power 0.33, which comes out to be 12.509 meter. So the abutment scouter, which many people had a doubt, in this question, is a very straightforward formulation, empirical formulation. 4 square root of 4h1 times uh, 0.33 of the approach Froude number. Let's take another question. A broad crested weir is built across a 45-meter wide river. The drop height is 2.5 meter and the face angle of the structure is 40 degrees. The scout slope is approximately 1 vertical is to 2 horizontal in non-cohesive material with D50 or the representative sediment dia as 2.5 mm. Estimate the scout depth when the river discharges 160 meter cube per second. So this basically comes from a very relevant question from Unit 6 or Unit 6 of our course of river engineering. So let us suppose we first of all want to know what is the discharge per unit width Q by W, and so Q is someone there to check. Okay, did someone try to enter? No, right? Okay, okay. I believe that no one tried to enter. I got a nice notification. So this would be 160 meter cube per second by the width of the flow is 45 meters, which will be 3.56 square meters per second. dp is 2.5 meters, that is the drop height, and the sediment representative dimension is 2.5 mm, which will be 2.5 into 10 power minus 3 meters, which is 0.0025 meters. Theta j is tan inverse 1 vertical times 2 horizontal, so it's 1 by 2, which comes out to be around 26 degrees. And phi, that is the face angle of the structure, is nothing but 40 degrees. So now it's a very straightforward question, by the way. Since we are moving into uh, very, since we are moving into advanced sediment hydraulics into this course, we need to understand a few or memorize a few empirical expressions also. So that is how this course is being designed. So HC, that is the critical depth, is Q square G by 1 by 3. That is the case for uh, critical depth of a rectangular section, which we already discussed in probably weekly session 3 or 4. So this will be 3.56 square by 9.81 power 1 by 3, which will be 1.09 meters. The approach velocity will be Q by SC, Why this? Because q is v1 times hc, just to maintain continuity. So this is q by hc equal to 3.56 by hc. Hc is 1.09 meter, and this is meter square per second. So this comes out to be 3.266 meter per second. We will take another slide to finish this formulation. So the question actually wants you to know the scow depth when the river discharges 160 meter cube per second. So we are indirectly finding out the discharge per unit width, and from that we will be finding out the scow depth from a very lengthy expression. This you will find in the unit 6 of the class lectures. So the expression is 1.8 times sine phi by sine theta j plus phi power zero point 0.8 times q to the power 0.6 v1 sine theta j by the specific gravity g minus 1 times g power zero point 0.8 times ds, the sediment dia, power zero point 0.4 minus the dv. So let us just put the expressions. A very similar question is asked in assignment number 6 also. And since it was, I mean, the assignment number 6 was posted today itself, so I thought of discussing the, I mean, toughest question in my opinion from assignment 6 in a by altering the numbers, or just to make you explain how this is to be found out. So 1.8 times sine 40 degree by sine 26 degree plus 40 degree power zero point 0.8 times 3.56 power zero point 0.6 into 3.266, which is a v1 approach velocity, times sine 26 degree by the specific gravity is in general 2.65. We know that already by, I mean, coming into the fifth unit of this course, into 9.81 power zero point 0.8 times ds 0.0025 meters power zero point 0.4 minus dp, which is 2.5 meters. So it comes out to be nearly 3.933 meters. Just count it for this case. Now, I mean, we have discussed five very distinct type of problems for this weekly live session. I would try to finish off this illustration part of the weekly live session uh, by showing the integral part of the continuity equation or the center variant equation, which is a combination of continuity and the momentum equation. Let's move into that. We'll take a few slides for that. Now let's see what is the differential form of the Saint Venant equation. Okay, I mean, you may be wondering why am I so curious about this equation? Because this happens to be the most fundamental equation for open channel flow, and you can ideally derive everything related to every expression related to the open channel flow through this equation, Saint Venant equation. It's very similar to the Navier-Stokes equation in terms of fluid flow. So it's a fundamental equation, and you need to know what it actually means. Okay, so the cross sectional area, let us suppose it's function of time. Okay, and the discharge of the flow of from the cross section, let us suppose it's a function of the length. Why am I coming into this is because its central line equation is nothing but del q by del x plus del a by del t. So it literally means that the discharge is a function of the position, and the cross sectional area is a function of time. It changes with respect to the cross sectional area. So let us suppose we want to know area, the cross sectional area at time t2. So how would we know that? We can utilize the Taylor's series expansion. So this would be a at t1 plus the first derivative del a by del t times delta t by 1 factorial plus the second derivative del 2a by del t square times change time change by 2 factorial, and so on, going into the higher order terms. Similarly, q at the position 2x2 would be q at position 1, that is a discharge at position 1, plus del q by del x times delta x by 1 factorial plus del 2 q by del x square times delta x square by 2 factorial, and the higher order terms. So what are these things actually? So delta x is the change in position, x2 minus x1 as we propagate further into a cross section, open channel cross section, and delta t is t2 minus t1. So we will try to come into the part of the Saint-Venant's generalized expression or its integral form. Let's see how it form out. So we can just neglect the higher order expressions of the representation for the cross sectional area and the discharge. Why? Why can we neglect that? It's because as the changes in the position or the changes in the times are very slow, these terms delta t whole square as well as delta x whole square will tend to zero. So we can easily neglect uh, the higher order expressions. Let me take another slide. Okay. So we neglect the second order term. Why? Because delta x power 2 and delta t power 2 will be almost 0. So we can do that easily. So the mass balance will be integral over change in the time, that is t1 to t2, and change in the position x1 to x2 of del a by del t plus del q by del x times dt dx is equal to 0. So this is the mass balance expression for the Saint-Venant's equation. Now we know that Saint-Venant's is just not the continuity expression. It also means that uh, momentum principle is to be satisfied. So we can similarly take or talk about the momentum principle. So the momentum principle becomes again the integral from time t1 to t2 and position x1 to x2 del q by del t plus del v square a by del x times dt dx x1 x2 t1 t2 minus g, that is the change in the forces or the terms which are on the right hand side of the momentum expression for the Saint-Venant's equation, del I1 by del x minus I2 minus S naught minus SF, that is the bed slope minus the friction slope, times A times dt dx. So we finally get the expressions del A by del T plus del q by del x equal to 0, which is the continuity equation, and del q by del t plus del by del x times v square a plus g I1 equal to g s naught minus sf, that is the bed slope minus the friction slope, times the cross sectional area plus gi. So this is the momentum part of the Sandman equation. So let us just see what I1 and I2 are. Let us suppose we are taking a very generalized cross section. We are not considering just a triangular cross section or a rectangular cross section or the trapezoidal cross section. Let's see how it's found out. Let us suppose the datum is here. So the datum head till the bottom of the cross section will be z naught. Let us suppose. So this is the free surface level where the top width happens to be capital B. So let us suppose this is y. So this would be d minus y because the total width. I mean, we are already. I mean, we are always using the same notation. I mean, throughout this weekly live session, that total depth of water flow happens to be small d, and let us suppose the total head. I mean, the water level depth plus the. Till the top of the uh, cross section happens to be capital Y. So I1, which we used a lot in this expression, just to simplify the momentum equation for the Saint Venant's expression. It would be 0 to d minus y times w dy. So this is d minus y, this term, times w, that is the cross section here, the top width here at this position, times dy, a very small incremental change in the position. And I2 will be 0 to d minus y del w by del x. What would be the change in the width with respect to the change in the position, times dy, where for this y is constant because it's change in the x direction and not the vertical direction. So this is how I wanted to explain the simplified expression for the integral form of the Saint Laurent's equation, which basically is two basic equations of flow through open channels. That is the continuity equation, which is mass balance, and the momentum equation. So, I will try to first of all give a small, give a brief about whatever we learned today, and then we will move into the assignments. If you have any doubts about the assignments, please ask me. And about assignment 4, we are actually intending to increase the deadline a bit because the options were not correct for a few of the questions. So the first question was a very simple one, to calculate the relative roughness, which we discussed today. It is not a function of the discharge. It is not a function of the kinematic viscosity. It is not even a function of the density of the flow. It is just a function of the undulation k and the depth of the flow. So that is what we found out. Then we found out the stream power per unit of stream length in watts per meters. So the expression is very simple, rho g qs. You just need to substitute the values and you will get the answer straight away. The third question discussed was, first of all, using a case of 90-degree notch angle for a triangular notch, and how we would find out the celerity. So we found out that the celerity for that case would be square root of g d by 2, where small d is the depth of the flow. Then we also chose a general case just to know how the notch angle would actually drive the celerity for a triangular cross sectional area. And we found that the notch angle does not actually play a part at all, because this the term containing theta by 2 gets cancelled. So the celerity is again square root of g d by 2. So irrespective of the angle chosen, the celerity will always be same for a triangular notch. Then we took a case of a trapezoidal cross section, and we understood that. We again took a very generalized case for any subtended angle for the trapezoidal cross section, which is termed as theta, and we found that for a trapezoidal cross section, the celerity happens to be a function of the subtended angle, unlike that of a triangular cross section. So C is a function of theta, because the the cot theta term does not get cancelled. Then we took a very simple expression for finding the celerity for a rectangular cross section, that is theta by square root of gt. Finally, we understood how the abutment scout depth is calculated, which is a kind of empirical expression. You need to remember this expression for it. The approach depth times the approach Froude number power 0.33 times 4 to find out the scout depth of abutment. Then we also understood how the scout depth is calculated for a broad crested weir, and we found that using a very empirical expression. This is relevant to assignment number 6. So while solving that, I believe now you should be able to solve it easily. And finally, we learned about the integral form of the Saint Laurent's equation. We derived it from the differential form from the very famous Taylor series expansion. We understood that for a higher order term, the delta t power 2 and delta x power 2 terms would be tending to 0. So we can just neglect the higher order terms, that is the terms with power 2 and greater, and we get a very similar or favorite expression of the Saint Laurent's equation for the continuity equation, that is the mass balance one, and the momentum equation. So this is how the Saint Laurent's equation is derived. Now, before ending the class today, I intend to discuss how the assignments are there. Let's see that. Let's start with assignment number 4. Do you have any doubts from assignment number 4?
The last question, sir. Last one.
Okay, so the last question actually requires the concepts of characteristic, characteristics, the method of
Mm.
characteristics, which would take me around 30 minutes just to explain that. So I plan to explain that in the next section, next weekly live session. Uh, it's a very conceptual
And
question.
even the last,
Yes, yes,
yeah,
please
yeah,
ask.
yeah. And even the last question of assignment 5 also, the answers may be not correct options.
Are the answers not correct?
Yeah, assignment 5, last question.
Okay, let me check. Okay, we will check it once. Okay, but you don't need to worry. In case you are not getting the correct answer,
Yeah,
we will be re-evaluating the assignment answers. Just like the
yeah,
case we did for assignment number 4. I discussed it with Mr. Mridhupavan Deka. So first of all, this is a wrong question. The answer
yeah,
is incorrect.
yeah.
Then uh, this is also wrong. Square root of GD
Wrong.
square does not make any
Yeah,
sense dimensionally.
yes, yes,
So this is
yes.
again wrong. I don't know how they are putting such options. No idea about that.
Yeah, and even the last one also.
No, no, last one is correct, by the way. I have checked it, but it would, I mean, in order to explain it in a nice way, I would require around 20 to 30 minutes just to explain the method of characteristics. It's a very famous method for open channel flow and in courses of advanced hydraulic engineering. But it would take me, I mean, just to start with the basics, it would around, I mean, take me around 20 to 30 minutes. So I thought of skipping it or discussing it in the next class. But this is a correct answer. 4.2 is correct answer.
But
What else? Are
thing is,
you?
in that one, actually the water is initially at rest, no, so that is misleading. So in the question, even if it is right option, so the
Yeah, so
question
you can
framed
take the
is
velocity to be zero.
yeah, but still, so if there is no velocity, then how the wave generates? No, that is conceptually not getting the
I
right
will explain
answer.
that. It is to be understood. I mean, how would it be zero? I mean, what if you open a search gate? It will. I mean, it will
Yeah.
change from zero to some other value, right?
Yes. Yes.
Let us suppose there is a mass of water at the upstream of a gate. So what if you suddenly lift up the gate? The initial velocity was zero because it was stored there. Then you will get some velocity afterwards. Isn't it correct conceptually?
Yeah. Maybe that way it is okay.
This
But
is a
the
correct
thing is,
question. This is a correct question, and this is actually the most interesting question so far in all the assignments. But in order to explain the method of characteristics, I mean, since uh, it is a very conceptual part, I would require you to, I mean, require to start from the very basics. So,
yeah.
uh, give me around 20 to 30 minutes in the next weekly live session. I will start with this question only because
Yeah.
this is,
And
I mean, the most
and the
conceptual one.
last one in the assignment 5 also, so please check the
Assignment.
answer. Assignment 5, last question. Assignment 5,
Okay, let me check.
last options given not correct.
Not correct.
Yeah. Yeah.
I will check it once. Okay.
Yeah. Yeah.
If it's incorrect, then we will again be reevaluating it. No need to worry about it. Okay.
Yeah, that one.
Please feel free to message me in case, I mean, you find some options to be incorrect. Then feel free to message me. Then from assignment 6, I discussed a very similar question as I think the second last question of the assignment. Yeah, a very similar question was discussed in today's live session. So, and this question is again being discussed in the previous assignment also. By the way, this apartment scouter. This is not a new question to you guys. You just need to
Yeah.
remember 4h1 times 4 fr1 times power 0.33. So you need to memorize a single equation and then you will be able to find it out. Okay. So h1 and fr1 will be the approach depth of the flow and the approach Froude number. Apart from that, every question is kind of conceptual. Okay. Uh, what else? Any other doubt from any lecture or any assignment so far? Please feel free to ask me.
There is a question, so maybe in the assignment 4 that they are given the shear stress and again asking some shear stress only. So that is question itself is not getting properly
Let me
understood.
check.
So maybe
Which one? Which one?
assignment 3 or 4.
3.
Uh,
This is assignment
shear
4.
stress, yeah, assignment 3, it seems.
Okay, let me check. Has Mr. Mridubhavan Deka uploaded the solutions, detailed solutions?
Please check that one.
I got a mail that he has uploaded the solutions, but I'm not sure about it. He
Mhm.
told me that he was about to upload it. Okay,
Okay.
which question are you talking about?
Shear stress, maybe shear, yeah, this one, you can check.
7.
It's question number 8, sir.
88 is. Shear
Okay.
stress is given and then asking for again shear stress. So not this one, sir. Other assignment.
If this appear as to the Froude number, where are they asking the shear stress again? Question number 8.
No, no, no. Other one, other assignment. So maybe 4. I'm not sure.
Let me check.
4.
But no
Please check.
need to worry if the answers are wrong. We are
It's
actually
in
continuously
assignment
assessing.
number 4, question number 8.
Yeah.
Question number 8. Okay.
So yes.
Okay.
Yeah. Yeah.
Okay. 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 I will. I will. I think I discussed a similar question. It was actually critical velocity most probably. sheer velocity most probably. I don't know. I mean, if there is anything wrong, please mail me. Okay. In case I don't want to forget. I mean your questions. So please mail me personally or even on the discussion forum. So if anything is wrong, we will be reassessing it. We actually plan to increase the deadline of this assignment to 29th. Let's see. Or in case you have filled wrong, option because of the incorrect options provided, we will be giving you full marks. No need to worry about that. That is under Mr. Deka actually. So he told me the same thing, that he has sent a mail to NPTEL IIT Madras to change the deadline. This happened to in a very similar course of Python, which is taken this year by NPTEL IIT Madras. So they increased the assignment because the questions were not correct. So Mr. Deka is actually the administrator. So he gets another option of reassessing the assignment solutions. So he has done that and he has sent a mail to the NPTEL administration. So no need to worry about it. Anything else from this weekly live session or some other weekly live session or anything else?
So as we discussed, so please give that summary, sir. Maybe at the end of the eighth
Yes,
week.
that
So
I
that
that
will,
I actually want to give in the eighth. The last
yeah,
weekly live session. Okay, so that
last week. Like,
yeah, so that just to end the course, I want to give it in a way that you will be understanding the important formulae and expressions. Okay.
yes, sir. Yes, yes.
So
That if we can
next
share
class I will
also. That,
start with method of characteristics, which is very
yeah.
interesting, but it's a bit hard to understand. So I will start
Yes.
with that, and I will discuss the last question of, I think, assignment number this assignment number 4 most probably. Yeah. Anything else? Are you able to grasp this course?
Yes, sir.
Okay, okay, nice, nice to know. Okay, so I think we are done for the day. In case you want to ask even now, please feel free to ask me. Okay, this is incorrect. This is incorrect, by the way. Any question from your side? No. Okay, then we shall call it a day. Stop recording.